Hi everyone, over the past few days I've been showing you working through examples of OLS estimates of linear regression models where we have two unknown parameters. I've picked this example to look at today because there are two things I can use to show you. One is what goes into the X transpose X matrix, and second is how to invert a 3x3 matrix. That second part is completely linear algebra. Okay, if you compare to the previous questions I've worked on, we're not given an X matrix and we're not given an X transpose X matrix, gram matrix. We're given instead all these sums. We're asked to compute the OLS estimates. There are three of them. Notice this is a linear regression model with no intercept. We can still use, this always applies for the OLS estimator given the standard assumption, so there we go. Well, that's the OLS estimator. But we need to construct the gram matrix, the X transpose X matrix. Okay. Now, first of all, just to remind you, let's do this in a different ink, that in statistics and econometrics, when we write down a vector, let's say X denotes a vector, we use it to denote it as we talk about a column vector. Okay, column vector. As opposed to a row vector, that if you do a mathematical methods course, they treat it as a row usually. Alright, so either way is fine, but we've got to understand how we're treating this thing. Treating each vector as a column vector. Right, we have three variables, x1, x2, x3. There are n observations. It tells you here there are 33 observations. So X transpose X looks like this. Right, so X subscript 1 is a vector. It's a column vector. So if I transpose it now, it becomes a row vector. So this is like 1 by n, so it's 1 by 33, 1 by 33, 1 by 33. This whole thing is a matrix 3 by 33. This is a column, 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 33 by 3. If we multiply it through, okay, we get this. So the 3 by 3 matrix, each of these guys are scalars. If we take this one, the element that goes in here will be the first component of the first row times the first column. That times that gives me that. Okay, to get this, it's this times this, and so on. Now I want to look a bit more into these scalars that go in here. It's related to do with notation. Let's pick this one. What does it mean to say this transpose times this? Well, it is a row vector times a column vector. We can rewrite that, if you think about it, as an inner product of the vector x1, x2. And that may be written like this. That's inner product. That's the inner product operation. So give you an example. Suppose x1 transposes this and x2 is that. Then what does it mean to say inner product? It means we write this down, and what does this, how do you compute this? We compute like this times that plus this times that, okay, which is this. So if you look at each of these guys in here, they are sums like this, which you can see in the question are these sums. So X transpose X in the product of 1 with itself is this guy here, it's 2. Okay, I've written it down right over here. 1, 2 is here. 1, 3 is over here. And so on. So you can write all that down. So that's the first lesson. The gram matrix, the constituents of the gram matrix are inner products. And we note that the gram matrix is symmetrical. We've got these numbers here. That is that. That is equal to that. That is equal to that. So indeed it's symmetrical. X transpose Y, similar kind of thing. So we have x1 inner product x1 with y, 5 inner product x2 y, 10, 3 y, 4. That's over here. Finally, we can just put them together. We need to find the inverse of the gram matrix, and this is a linear algebra thing, and I'm going to show you how to do it. But it turns out to be this here. we have to invert a 3 by 3 matrix, times this, and this is the answer. Okay, that's the end of part 1, and that's about basically the components of the gram matrix. Now part 2, we're going to go into inverting a 3 by 3 matrix. If you're not interested at this stage, obviously I've showed you conceptually what's going on there. You can kind of see you on another video. Otherwise, here we go. The method of finding the inverse of a matrix, square matrix. Well, guys, on a linear course in linear algebra, you'll probably seen two methods: the Gauss Jordan elimination, probably the first one you see. That's where you use the row operations going from over here to over here. And some of you are taught the method of cofactors. Right, I've kind of given myself the task to show you for this question both of them, and then I'm going to kind of just compare both. If you're only interested in seeing one of these methods, what I'm going to do is in the description box I put a timeline so you can just click on that to get to the relevant part of the video. Alright, in our question we want to find the inverse of this. So let's first of all use the Gauss Jordan elimination. I need to write down this first. Can I just say I got those the wrong way around? This is the standard way to write it. So you know that's the thing I'm going to act on. It's going to act on the right hand side as well. I'm going to go over here if the inverse exists. Right, to go from here to here, we may perform any of the three operations. You can take notes if you need to here. I'm not going to write it down. We may multiply a row by a non-zero constant. You may interchange two rows. Thirdly, you may add a multiple of one row to another. The strategy here is to, since we want leading ones on the diagonal here, because we've got to turn this thing into identity, we want ones along here, zeros up above and zeros below. We're going to work on turning the first thing into a 1 and everything below into a 0, then work on this one, turn that to 1, 0, and then that should be a 1, and everything above it zeros. The thing about this is there's no one way to do it, okay? So you just know strategies, there's like no correct way, you gotta do it exactly this step followed by that step. I'm going to interchange rows 1 and 2 because I'm going to get rid of that 2. I mean I could do it with, yeah, I'm going to do 1 and 2. Okay, interchanging both rows, that's on the left and right side of this vertical line. So I get that. That's the change. Next I'm going to make both these zeros. I'm going to multiply, say, third row. If I look at it, I can multiply -1 to the first row and add it to the third row, and also I can multiply -2 to the first row and add it to the second row to turn that into 0. Next, I'm working on column 2. I want a 1 along here and 0s below. I want to simplify some numbers. I mean, I could divide row 2 by -19 right through, but then I'm going to get fractions, and the thing is, if you're doing this by hand, you want to leave fractions to the end as possible, because when you've got fractions it makes things a bit more fiddly, and every single step you do there's increased chance of making an error. So what I can try to do to simplify the numbers here is multiply row 2 by -1 and just add it to the third row, just to get the numbers down a bit. Okay, that's what I've done now. And if you're looking very carefully, you'll say, oh, why didn't you switch row 2 and 1 at the beginning instead of 3 and 1, whatever I did, right? Because look, if I look at this now, it looks like with row 3 I should divide that through by 1, then this will be a 1, and I've got zeros here, and then that means these two I should be able to interchange. Okay, I've divided row 3 by 9. With the first row, what I'm going to do, because get rid of that 10, multiply row 3 by -10 and add it to row 1. Okay, that gives me this. And to get rid of that 19, I'm going to multiply row 3 by 19 and add it to row 2. So now you can see that pretty much I've got that. I just need to swap rows 2 and 3, and then on the left hand side I will have identity matrix, and then this guy will be the inverse. Notice this common factor of 1 over 9, so I can bring that out and just copy those numbers in, and that's my inverse. Tip on this is, so work on each column, making the leading one below the leading one zeros and working across to the right. Don't worry about being the correct way, because there isn't a exactly correct step. So long as you follow the 3 operations, you should get there. And fractions, yeah, if you need fractions, leave it the latest day as possible. Okay guys, method of cofactor to find an inverse of a square matrix. First we need 4 things. First recap, recall that the determinant of a 2 by 2 matrix is just this. Next, I'm going to define something called the minor. The minor, the ith minor of a matrix is a determinant after removing the ith row and jth column. Okay, so what's left after you remove the ith row, jth column? And denote that like this. The ith cofactor, denoted by this, is basically the signed, is like the signed minor. So for a 3 by 3 matrix, the signs look like this, because this is, for this one, it's row 1, that's I equal 1, column 1, that's j is equal to 1, well, minus 1 to the power of 1 plus 1, that's up to 2, is plus 1, and so on. Just know that they alternate, beginning on the top left by plus, and you'll be fine. Finally, the adjunct of this square matrix N, denoted like this, is the transpose of the matrix of cofactors. Now, I had to use all its jargon because it makes it easy to present. Then we know this key result, that the inverse of a matrix A, if it exists, is equal to 1 over the determinant of A multiplied by the adjunct of A. Now this thing is an algorithm, so there's nothing to understand, guys. So first, finding the determinant of A, I'm going to use the cofactor expansion, and I can expand it by any row or column. I'm going to do it by row 3 because it's easy to compute. Right, so I've got to explain what this expansion is. What you do is you pick a row. I'm picking third row. Right, I take that number and I multiply it by the cofactor for that row and that column. So it's 1 times the cofactor for row 3, column 1, plus, and then I go to the next element, that number, it's 0 times the cofactor for that row and that column. C3, that's third row, second column, plus that number, 1 times the cofactor for that row that it's sitting in and the column that it's sitting in. 3. Good. Remember now, these cofactors are just signed minors. Right, so we know that that's a plus, minus, plus. So it's going to be a plus that sits there. It's going to be a plus, minus, plus. Let's just kind of remind ourselves, plus, minus, plus is going to sit there. So we're going to have a plus, minus, plus. 1 is going to be a plus, times a plus. Cofactor for 3, 1. So that's just this. I get hold of the minor. So take that row out, take that column out, and find the determinant of what's left. Determinant of what's left is 1, 10, 0, and it's a plus there. That says multiply, and it's, yeah, the whole thing's a plus. Plus 0 times whatever that cofactor is. It doesn't matter because 0 times a number. A cofactor is just is going to be a number here. 0 plus 1 times cofactor for 3, 3. take that out, you're left with this determinant of this, and it's a plus sign for the minus, so there you are, that's the cofactor. And this is, we could work this out, 1 times 0 minus 10 times 1. That's equal to 9. The determinant does not equal to 0, and that means that the inverse exists, right? Remember that rule? So inverse exists if and only if the determinant of this matrix is not 0. So if it was 0 here, we just stop here and we know that there's no unique solution for our problem. Next we want to find the cofactors. Remember, the cofactors are linked to the minors because they're just some plus or minus and minor. So let's just write down the minors. So for row 1, column 1, definition of minor is take that row out, take that column out, and determine what's left. Okay, 10 minus 0, 10. And we do it for each. How many times do we have to do it? We have to do it as many numbers as are here. So you have to do it 9 times. Let's pick another one. Row 1, column 2. I take that out. So in other words, I take a t out of it. That's 1, 1. On the left and on the right hand side, I've got 0, 1. Being this and that left. That's 1. And continue. So just have a go. Don't just watch. So check that you get these numbers. To save yourself some time, note the off diagonals, this cofact matrix, these minors are matrix of minor, symmetric. So row 1, column 2 will be the same as minor of row 2, column 1. Okay, finally step 3. Oh well, almost there. Write down the adjunct of the matrix. Remember, adjunct is defined as the transpose of the matrix of cofactors. So my rows becomes columns and my columns becomes rows. So that's the first row. Before that was the first column, now it's become a row like that. It's linked to the minors being the sign, so I've just written this in red so you can see I've got these minors already, and I just substitute in the numbers. Finally, so I take the adjunct, which is this, and I divide it by the determinant, which I showed was 9, and that's the inverse. Done. So I've just shown you another method, the method of cofactors. It's basically it's an algorithm, basically nothing to understand, guys, and that's why it's a bit of a pain. You can't really, it's just like memorizing it. How can I help you to memorize this thing? I'm not sure. You've got to find some way. So you know it involves, first of all, you need to find, after the determinant, you need to find the minor, you need to find a cofactor, and then find adjunct, then you put it together. So I don't know, how do you pronounce that? Misha? YMCA, if you forget that. Anyway, however you memorize it, it's those steps. Final remarks, right, on finding the inverse of a matrix. I thought I'd only do one, but I thought it's better for you guys if I do both, then you can see how much I struggle with it, or see which one that you can look at and say, oh god, I obviously prefer this way to that way. Observations: the Gauss Jordan elimination is the one that you're most likely to be taught first. It is general, you can apply it to 3x3, 4x4, however many you like, okay? So too, you can do it with method of cofactors. The thing though with cofactors is that as the matrix gets bigger, the method gets more complex than the Gauss Jordan elimination. Computers use the Gauss Jordan elimination. As the matrix gets bigger and bigger, 3, 4, 5, 600 by 100, you know, the Gauss Jordan elimination becomes much more faster to run than the method of cofactors. With that observation, you can see that if you had to just learn one of them, the Gauss Jordan elimination is the easier one to memorize and the most general, because it works for, you know, any size, and also you only have to remember the 3 row operations. The method of cofactors, although it works for 3x3 pretty nicely, once you get beyond, like, you get 4, 5, 6, and 4, 5, 6, it's going to be a complete mess. And also you've got a lot more things to memorize with this method of cofactors. Having said that, my experience is like, okay, so we've got a 3 by 3 matrix. Using the method of cofactors, it kind of just breaks everything down into small, neat little bits to calculate determinants of 2 by 2 matrices, which you can do in your head very quickly. In Gauss Jordan elimination, you see each step you've got to be kind of careful when you're going from one operation to another. You can make a small mistake, everything is out, and it's so easy to do, so you've got to take your time. Having said that, it might be your experience that you just it's a breeze to do the Gauss Jordan elimination, in which case stick with that. Unless, of course, your professor says in an exam paper, do it by a method of cofactors. So how do you find it? Share your experiences. See you later on the next video.